ready to come back for another day of programming on oil. We have improved our system somewhat since yesterday. We now have a very high-tech timing device. In the front here, we have time cards. And hopefully that'll help us keep a little bit more on track than last time. We're starting, as you can see, very slightly late. We're going to shift everything back 15 minutes so the panel gets as much time as it deserves. Without too much further ado, I'm going to introduce our moderator and first speaker, Professor David Archer, who is from the University of Chicago right here. So, Professor Archer.
Thank you very much. I'm honored to be invited to speak here, and indeed the donut was delicious this morning. I commend you on that. So I'm going to speak briefly about the issue of petroleum from my perspective as an earth scientist, and in particular as someone who has written and taught classes about the issue of global warming. So my scientific specialty is actually ocean chemistry, carbon chemistry of the oceans. I'm not a petroleum geologist. I guess I'm not really a geologist at all. So some of the people that you're going to hear from know more about the geology of petroleum than I do. So you have to take into account the source when you're listening to anything that I say about oil. So this is a plot from a textbook that I just published about global warming, about the different sources of energy used by different countries around the world. So you can see, let's see, oil is the one with the sort of diagonal dashes there. And you can see that petroleum accounts for about a third of global energy use, kind of more or less. And that's true in the United States as well. And the fraction of energy provided by oil varies from country to country a little bit, but not all that much. Oil is a sort of mainstay of energy supply pretty much wherever you look. This is what oil is used for in the United States. It's almost entirely, well, dominated by transportation, which makes sense because oil is a very convenient form of energy to carry around and put into a motor. You can't really throw coal into an engine these days. The way engines work, it would kind of gum up the works. And if you want to use natural gas for transportation, you'd need a big cylinder of some sort to keep the gas from expanding, whereas a liquid petroleum is just an ideal transportation fuel. The climate impact of the different fossil fuels varies a little bit because of the different energy contents of the fuels relative to the carbon. So coal is the least efficient in that regard. You can see it has the largest number of gigatons of carbon released per terawatt of energy produced of the fossil fuels, and that's because coal is almost, it's sort of elemental carbon, and so you basically have the carbon going to CO2, that's where the energy comes from. Whereas the oil and gas have hydrogen in them as well, so the hydrogen makes water, so you get an extra boost of energy that way. So in terms of the carbon emission, oil is kind of in between the other two sources of energy. So here's where I'm stepping onto ground that I don't know as well as maybe some people here do. But oil is very, very special fossil fuel. It takes just a whole series of fortunate events in order to create oil out of dead plankton in the ocean. For one thing, the source rocks that are used to make oil are extremely sort of rare in the world. In Wyoming, I was just reading last night, there's 20,000 feet of sedimentary rock sequences, and only about 30 feet of that are the oil source rocks that are responsible for the oil fields in Wyoming. The Middle East is entirely, the source rocks are just 100 feet thick, just very, very special rocks. And then the rocks have to be cooked up just right, so they have to be buried to depths in the earth between about 7 and 15 kilometers to get the temperature right to cook and produce liquid oil from the dead plankton in the sediments. If it's cooked too hot, if it's buried too deeply, it'll transform into natural gas and it won't be petroleum anymore. And then the oil has to be mobile and be able to leak out of the source rocks, and then it has to be trapped someplace. I would imagine that probably the vast majority of oil ever produced in the earth it has either leaked out to the surface, like the beginning of the Beverly Hillbillies when there was oil coming out of the ground when Jed Clampett was out shooting up some food, or else it might just be sort of in pores of the rock and not mobile enough to ever collect. So it's an extremely special series of events that take this dead plankton and put it into a convenient reservoir that can be tapped to get oil. As a result, because sort of the statistics of small numbers, the oil distribution around the world, I'm not telling you anything you don't know, is extremely patchy, and most of the oil reserves are found in the Middle East. So this is a plot, according to British Petroleum, where the oil can be found. So you heard something about this last night. You'll hear more about it today. The idea that the discussion about how long the petroleum reserves will last, how long we can count on oil. So this is a famous plot of Hubbert's Peak, which is based on the amount of oil, the rate of oil extraction from the continental U.S., the 48 states. And so in 1950-something, 52 or something, Hubbert made this prediction that, so he noted empirically that the rate of oil extraction from an oil field tends to follow a sort of a bell curve like this. And he took the total amount of oil that he expected in the lower 48 states and fit the historical data in 52 to the shape of a bell curve where the total inventory is the area under the curve. And he predicted a peak right around the 1970. And he did that in a time when it looked like things were going to keep going up forever. And he called it right on. So I imagine the guy must have been a great miniature golfer to be able to, see that one coming in advance. Maybe he was just extraordinarily lucky. I don't know. So where we expect the peak to come for oil, the world oil supply depends on how much oil there is, which sort of depends on improvements in technology and what we call oil. So if we say that there were 200 gigatons of carbon in oil, then we'd have the peak pretty much right about now. If we start counting oil shales and tar sands and things like that and increase what we call oil to 500 gigatons, then the peak could be several decades from now. And here, just for fun, is a Hubbert's Peak for whale oil that I found on the internet and got permission to show in my book. So you can see the extraction rate of the whale oil. Sort of, there's a ramping up period, and then a peak, and then a decline as the whales became depleted, I suppose. And then at the top panel, you can see the trading cost of whale oil goes up after you pass that peak. So I guess the essential thing about peak theory is that the shortage starts to happen when about half of the resource has been extracted. It's not when the last drop comes out of the ground that's important, but when half of it is gone. Okay, so now to the issue of climate change. When CO2 is released to the atmosphere, it has a series of places that it can go, a series of processes that will sort of mop up the CO2 out of the atmosphere. The largest one, and actually one of the quickest ones, is for carbon dioxide to simply dissolve in the ocean. And that has a time constant of several centuries. Different models have slightly different uptake time constants. You'd think it would happen very quickly because 70% of the Earth's surface is covered by water. It looks, it's a blue planet after all. But the way the ocean circulates, the only way to replenish the waters in the deep ocean is through very small windows of the surface ocean in the high latitudes. You have to make water that's very cold in order to displace the cold water that's already down there. So it takes centuries to get there. The terrestrial biosphere, the trees and soil carbon, also have an impact on atmospheric CO2. Today, the land carbon is sort of a wash. We're cutting down trees in the tropics, but yet there's sort of a mysterious uptake of CO2 in the high latitudes, which is some sort of CO2 fertilization of the forests or longer growing season or maybe fire suppression. It's hard to know what the cause of that is. What the terrestrial biosphere will do in the coming century is one of the larger uncertainties actually in the global warming forecast, whether it will continue to help us out or whether it will start being a positive feedback and releasing carbon to the atmosphere. And then after those processes are done, after they've sort of inhaled their fill, there is neutralization of the CO2 by dissolution of calcium carbonate. So CO2 is an acid, calcium carbonate is a base, and they react together to make a salt, which is actually bicarbonate in the ocean. And that takes up a fraction of the CO2 on timescales of thousands of years. And even that leaves behind a residual amount of CO2 which reacts with igneous rocks on time constants of hundreds of thousands of years. So the overall picture looks something like this. This is a time course of CO2 in the atmosphere going 40,000 years into the future. The fossil fuel era is that spike at the beginning, and then it goes down, most of the way by dissolving in the oceans. But then there's this long tail that kind of is left behind. So not necessarily all that apropos of petroleum, but this is sort of my Carthage must be destroyed moment. Here's an intelligent audience, is something that I want to tell people about. The long times constant of the CO2 in the atmosphere, so it's just a tangent, indulge me for 2 minutes. The long time scale of CO2 in the atmosphere means that the sea level response to the CO2 is actually going to be vastly greater than what you read about for the forecast for sea level rise in the coming century. So the plot here shows changes in sea level in geologic time in the past, plotted against global average temperature in the past. So in the lower left, you can see the last glacial maximum 20,000 years ago when sea level was 120 meters lower than today and temperature was 5 or 6 degrees colder. Present day is right in the center there. And then times even earlier than that in the deeper past when sea level was higher and the temperature was warmer than today. So there's a whole world of complexity, and people spend their lives studying dynamics of ice sheets and things like that. And I don't mean to denigrate their work, but there is also virtue in just sort of connecting the dots, and you see this sort of relationship between global average temperature and sea level on geologic timescales. And then for contrast, in red, you see the forecast for sea level rise and temperature to the year 2100. 3 degrees C of temperature under business as usual, and maybe a half a meter of sea level rise. And you can see that that's way off of the line from the geologic past, and that's because it takes longer than 100 years to melt ice sheets. But CO2 will be around for thousands, tens of thousands of years, plenty of time to melt even the most sluggish ice sheet model. And so on the longer time scale, we're talking about tens of meters of sea level change. Okay, that's the end of my little soapbox. So this is now a series of model results of how much CO2 that we release to the atmosphere from fossil fuels will still be in the atmosphere as a function of time in the future. So the first column there is supposed to say peak, and that's the CO2 concentration at its highest level, and that usually comes right at the end of the fossil fuel release era. So it's going up as we're pushing it up, and then ultimately, presumably, we stop, and then it starts coming back down. So the maximum fraction of CO2 in the atmosphere is 50, 60, maybe 70% of the carbon that's released. Actually, that's how much of the fossil fuel that has been released so far is in the atmosphere today as well. It depends a little bit on how much is released. So 4,000 or 5,000 gigatons of carbon, that's basically all of the coal. So if we decrease the amount of carbon that's released, 1,000 to 2,000, that's kind of IPCC business as usual scenario to the year 2100. So by the year 2100, the oil and gas what we call an oil and gas today will presumably be gone, but there will still be coal left. So these would be sort of business as usual to then, but leaving coal in the ground, I guess. So the smaller carbon release, it acidifies the ocean less, it changes the chemistry of the ocean less, and so the ocean actually can take up more carbon. And so you see in the peak, the numbers are a little lower, 50 to 60% instead of 70% for the larger releases. All right, so here's the meat of the global warming argument here. Let's say at the atmospheric peak, the highest CO2 concentrations that you have, there will be 50% of the emitted CO2 in the atmosphere at that moment. And talking about avoiding climate change, a lot of times what's done is to pick out a temperature that you say is a danger limit, and what would it take to avoid exceeding that danger limit. And, you know, it's a judgment call, and I get picked on from both sides of the spectrum when I talk about these numbers, both people who say that the danger limit that I would pick out is, or at least that I'm talking about, is you know, too dangerous or too conservative. But 2 degrees C is taken as a danger limit, basically based on the recent geological history of global temperature. 2 degrees C would be significantly warmer than the Earth has been in millions of years. And so if you start venturing into climates that you haven't seen in millions of years, you're really venturing into the unknown. So are there different ways for the ocean to circulate, different climate states? What is the rainfall patterns in a world like that? We don't really know. So just for a number to talk about, if we say 2 degrees C is a danger limit that we would like to not exceed, we can use that to try to constrain how much CO2 we can release. The last ingredient is the climate sensitivity of the Earth, how much the temperature changes for doubling CO2. So the latest IPCC report has a 95% confidence interval of 2 degrees to 4.5 degrees for the climate sensitivity of the Earth. And that's based on studies of past climate changes, the last glacial time, the climate just of the last decades. A whole slew of studies kind of converge on that range. Okay, so if we put those ingredients together, we come up with the total amount of CO2 that can be emitted to never exceed that 2 degrees C danger limit, and it comes to about 700 gigatons of carbon. So how much is that? We've already emitted about 300 gigatons of carbon. And then the fossil fuel inventories, and here there may be discussion about, you know, bigger or less, but, you know, typical estimates of that: oil, maybe 250 gigatons left. Gas, maybe 100 gigatons. Coal is the big reservoir. There's 5,000 gigatons there. There's also a huge potential reservoir, came in conversation about this morning, of methane in the ocean, which is not currently viewed as a fossil fuel resource because nobody knows how to get it, but that could be 5,000 gigatons as well. So those are the scales of how much fossil fuels there are, and you see that oil is kind of small potatoes compared to coal, and also compared to, you know, we can release another 400 gigatons and avoid sort of the really catastrophic climate change. So one conceptually very simple solution to the whole thing would be to burn all the oil and gas we can find and just stop burning coal today. Really, there's not enough oil in the ground unless, you know, this is a horribly mistaken estimate, to totally cook the planet. Really, the question about global warming, I think, comes down to coal, the first question. So to sort of sum up what I just told you, oil today seems like it's an important part of the global warming question because it contributes about 1/3 of our carbon dioxide emissions, something like that. But the oil, from the perspective of the Earth and global warming, it seems like the oil will be gone soon enough. So we're going to have to deal with how to, you know, drive cars with something other than fossil fuel petroleum soon enough. And so I think, you know, the strongest reasons to deal with that sooner than later may come from the political side that are sort of the focus of this meeting. From the global warming side, the most important issue is to stop building these coal-fired power plants and start coming up with other ways of getting energy out of coal and sequestering the carbon, or coming up with different ways of getting energy that don't use carbon at all. So that's what I came to tell you. Thank you very much.
Good morning. It's a pleasure to be here this morning. I'm originally from Chicago, and it's always good to be back. I want to do a couple of things here this morning. Talk about the peak oil theory or hypothesis that you've heard talk about somewhat last night and just now. Talk about oil supply and demand forecasts and what they imply. Spend a few minutes talking about natural gas and see if that's our savior, as some people think. Then talk about oil imports and national security and mitigation options, how we want to get away from continued increasing dependence on oil imports and energy imports. And then finish up talking about mitigation, quote unquote, whatever that means, as a bridge to the new energy economy, whatever and whenever that may be. We're facing an energy crisis. No, what we're facing is a liquid fuels crisis, primarily, as a number of speakers have noted, in the transportation area, because transportation is very heavily reliant upon petroleum, and a larger and larger fraction of our oil use is being consumed by the transportation sector, and there are at present few alternatives. Well, the peak oil theory has been called, quote, nonsense and garbage by supposedly knowledgeable people such as Michael Lynch, Daniel Yergin, and others. Is it? Maybe not. When understood correctly, when people talk about peaking, talking about the maximum production of conventional oil, not running out of oil. The world will never run out of oil. As an economist, I'm not all that comfortable with the term. I prefer to say that really the problem we're facing in the present or very near future is that the demand for conventional, relatively cheap oil is simply outstripping the demand, and maybe that way for decades to come. Yes, there were many predictions over the past year of the world running out of oil. Most of them were wrong. Hubbard, as we just found out, made the prediction in 1956 that U.S. oil production would peak in 1970. He was spot on. Why are we reconsidering peak oil or peak oil problems now or the past 3 or 4 or 5 years? Well, there's a number of reasons. As we'll see in a minute, world oil consumption is vastly outstripping discoveries. Many countries, there's about 70, 75 major oil-producing countries in the world. Somewhere between 55 and 60 of them have already peaked and are in decline. Capital expenditures for oil and gas, and in fact for almost any type of energy projects, are large and growing. There's an extensive database worldwide drilling. We know a lot more than we did 10, 20, 30, or 40 years ago. There's been incredible advances in technology, 3D, seismic, et cetera. I'm not a petroleum geologist or petroleum engineer, but a lot of the top people in the field are extremely pessimistic. The large giant and supergiant oil fields have pretty much been discovered. Last supergiant, I think, was 1967 in Saudi Arabia. Those are the easiest, the most productive fields. It's not like people have not been looking for them. Finally, and certainly one major reason that we have to reconsider this, the economic consequences, potential consequences of demand outstripping supply are huge, very significant. Okay, why will oil peak? The upper left is a production profile of a typical oil well. You aggregate hundreds or thousands of these, you get a typical oil province, such as the U.S. lower 48. You aggregate dozens or hundreds of oil provinces worldwide, and the world oil peaking situation may look generically something like what the U.S. lower 48 looked like. If you take one or two things away from my presentation, take an image of this chart. This was given to me by Jim Schlesinger, our next DOE Energy Secretary. Simply it shows that for the past 20 years, world oil consumption has been outstripping new oil discoveries. The world is presently consuming somewhere in the range of 4 or 5 times as much oil every year as is being discovered. Whatever you wish to call whatever you wish to call it peak oil, call it the demand outstripping supply. For the past 20 years or so, the world has been consuming a lot more oil than has been found. The gap is increasing. Eventually, someday, be it next week, next month, next year, or 5 years, or 10 years from now, reality will bite and there will be a problem. This is the USGS relatively recent likely forecasts of world oil reserves. I just note that the yellow yellow dotted line at the bottom is the 95% probability. That's the most likely. If you want to believe that the upper blue dotted line will come true, there's one chance in 20 or one chance in 25. It's the 5% probability. People have unfortunately focused on the green line or the blue line, not recognizing that the yellow line is much more likely what's likely to happen in the future. Basically what happens after discovery declines, production inevitably declines about a quarter century later. This is simply the situation in Norway. Discovery peaked about 27 years before oil production in Norway peaked, which happened about 2003, 2004, and it's on a constant decline. This happened in the U.S. It's happened in 55 countries already, including some countries who used to be in OPEC. Production peaks can be sudden, sharp, and not necessarily similar. You see what happened in Texas, North America, United Kingdom, and Norway. False peaks, multiple peaks, maybe some plateaus, but the bottom line is that production increases, reaches a maximum or plateau, and then it declines in some cases very rapidly. And I might note that these drastic declines you see in production in the United Kingdom and Norway have happened in the past 4 or 5 or 6 years, over time when oil prices have essentially tripled or more. So increased oil prices may not necessarily result in increases in oil production. It may not be enough to stop the decrease. Which is illustrated in this slide is the U.S. production profile. Again, it peaked in 1970, has been going downhill ever since, and every forecast says it's going to continue to decline forever, basically. And what's happened over the past 3 decades, we've had huge swings in prices. You've had tremendous increases, enhancements in oil field technology. None of this has arrested the decline in U.S. oil production. Technology and price may be able to help, but once an oil field or reservoir or region or province begins to decline, it doesn't stop declining. These are some recent forecasts of when this crunch may come. Already soon, within 5 years, 5 to 15 years. Bottom line here, I think, is that because of inertia on the infrastructure and existing vehicle fleet and capital equipment, if we expect to see peaking any time in the next 15 or 20 years, it's almost too late to avoid some serious problems because it just takes decades and trillions of dollars to mitigate the situation. There's been some discussion of how much conventional oil is left. Everyone seems to agree that we've consumed thus far about 1 trillion barrels. Some say that there's maybe another trillion left, which means we're at or near peaking. Some people say it's closer to 2 trillion. The EIA, the Energy Information Administration, looked at this and basically found that even if there's an additional 2 trillion barrels of conventional oil left, it only decreases or increases the year of peaking by about a decade, which is illustrated in the following graph. So even gaining an additional 1 trillion barrels of conventional oil delays peaking by something in the range of 10 years. So instead of from 2008 to 2018. And again, even if you believe this very optimistic case, because most petroleum geologists don't believe this, peaking could happen as early as 2017, 2018. What happens at peaking? Well, supply cannot keep up with demand. Prices increase, shortages develop, quote unquote. There'll never be a shortage of oil in the short term or the long term. There'll be some market clearing price, whether it's $100 a barrel, $200 a barrel, $500 a barrel. The world's economies may end up in the tank, but supply and demand markets do work. In the 1970s, the good old days of stagflation, recession, that was a temporary disruption, even artificial in terms of an artificial supply interruption. We're talking about world oil production peaking. We're talking potentially about decades of problems, much more severe than we or the rest of the world experienced during the 1970s. Yes, demand destruction will always equate supply with demand, whether it's relatively minor demand destruction or major. But demand destruction, as I'm fond of telling people, is nothing but a euphemism for recession, unemployment, depression, and so forth. I've been in many debates with people who seem to think that demand destruction is the solution. I look upon it as the problem. If you want industry to go into the tank, you want unemployment to increase dramatically, interest rates, and so forth. That is what the demand destruction gives you. It's a thing we should be, I think, be trying to avoid with fairly intelligent and timely mitigation initiatives. Natural gas to the rescue. Everyone from Alan Greenspan on down in recent years have said that we can rely on imported LNG to solve our problems. Maybe, maybe not. Let's look at the recent natural gas forecast. This is from EIA, but they're not the only one. Just a few years ago, there are a large number of experts telling us that in the U.S., we could look forward to vastly increased supplies of natural gas at relatively reasonable prices. Well, in a period of 3 or 4 years, those forecasts have been revised dramatically downward. Bottom line here is, forecasting oil supply is indeed very difficult. Even the more recent forecasting assumptions need to be assessed. EIA is forecasting natural gas prices to decline, but supplies to increase and demand only change modestly. Anyone who's had Economics 101 should question that. If prices are declining, why should supplies be increasing for the next 15 to 18 years? This may be more likely the natural gas situation in the U.S. over the next decade or two, simply increasing shortfalls. For the past 6 years, U.S. drillers have greatly wrapped up drilling, but production has not followed, which indicates that the U.S. natural gas production has peaked, and so also has Canadian natural gas production. Every year, again, EIA has been ramping down their forecasts of likely future U.S. natural gas production. Canadian production has also hit a wall, and talking to some people in Canada, the situation there may be even worse than in the U.S. And since the oil sands production in Canada requires incredible quantities of natural gas, that may serve as a limit as to how much liquid fuels from oil sands we or the Canadians or anybody else is likely to get in coming decades. The power sector in the U.S. anyway is the key. What happened in the late 1980s to just a couple of years ago, almost all new electric power generating plants in this country were natural gas fired. Many of them now are shut in or stranded assets because as the price of natural gas doubled, tripled, and quadrupled, they couldn't afford to generate electricity anymore using natural gas. Basically, we're down to two assumptions for adequate supplies and prices of natural gas. The Alaskan natural gas pipeline by 2018, which is increasingly questionable. Until then, we're dependent upon LNG, assuming we can build a terminal, assuming there's be available at reasonable prices. Even assuming that, just think one thing. Are we really comfortable with becoming reliant upon imported LNG from the same regions and countries we're now worried about importing oil from the Middle East, Russia, and so forth? I think not. The scale of the problem, this is a little exercise we did for DOE last year. President Bush says reduce our dependence on imported oil. DOE said, ask us what would happen if we just held it to 205 levels. That would require us by 2025 to increase our liquid fuel supplies by 5 million barrels a day, which is about what we're going to be producing domestically in that year. It's 5 times what is produced in the country of Australia. This is not to reduce our import dependence, just to keep it constant. This is an exercise we did for the Southern States Energy Board last year. Starting at 2030, if we want to reduce or eliminate oil imports, these are the kind of contributions you need from the options: energy efficiency, oil shale, enhanced oil recovery, biomass, coal to liquids, and so forth. You can argue with these wedges, the size, the shape, they're phasing in, phasing out, whatever, but there are only so many liquid fuel options we have, and it's a zero-sum game. Coal is our most abundant resource, and I think we're going to have to find some way in a carbon-constrained environment to use it both for electricity production and for CTL, coal to liquids. We have oil equivalent coal in this country, twice what the current oil reserves in the Middle East are. A number of studies been done over the past year of potential of coal to liquids. Achieving something like 5 million barrels a day by 2030 is under a very aggressive scenario. It may be technically, economically feasible. Coal to liquid plants simply look like large refineries. This is the CTL rollout in the Southern States Energy Board study I mentioned. Starts very slowly, then has to ramp up very quickly to get to the year 2030. We did this for all the options we looked at. I'm just using CTL as an example here. The economic impact of the initiatives can be significant, but that's true of most of the options we look at. You're investing literally trillions of dollars into these energy mitigation options. They'll have a lot of peripheral benefits aside from just decreasing U.S. Oil imports. The mitigation will have to be the bridge to the new energy economy, whatever that may be, and I think we should look upon these mitigation options on both the supply and the demand side to smooth phasely over time to avoid the kind of economic problems I mentioned earlier. This just gives some decline rate, hypothetical decline rates for oil and indicating how much you can save or produce with different options X years into the future. It's my next to last slide, and I just want to spend 1 minute on it. It's very important. People talk about transitioning to a new energy regime, a new energy economy over a certain period of time with certain options, which is all, which is very good and very important. But you have to step back and say, where do we want to be? Do we want to maintain the current energy regime infrastructure? 230 million vehicles today, 500 million or 400 million vehicles in 2030. We want them to all run on biofuels, on petroleum, on coal to liquids. Do we want them to get 100 miles a gallon? Do we want hybrids? Do we want plug-in electric vehicles? If so, define your endpoint, then define how you're going to get there. When you're going to get there? 2020? You can't. It's already too late. 2030? Maybe. 2050? Possibly. Then work backwards. How many decades will it take to get there? How many trillions of dollars of investment will it take? And what kind of changes in, quote, lifestyle will it require? And don't tell me everyone will be taking mass transit or walking to work. That's simply not feasible. The estimates are that within 35 years, the U.S. population will increase from 300 million to 400 million. All those people will be driving vehicles. They'll be flying in airplanes. They'll have plasma TVs, want their air conditioning, and so forth. Figure that into the equation when you're talking about reducing U.S. oil dependence, oil imports, CO2 emissions, and so forth. In conclusion, there was the major finding of all of our work in recent years that there's no silver bullet, there's no magic painless solution. It'll take all the options on the supply and demand side that I've talked about and many more over many decades to get us even half the way where we want to go. Absent that, unless we start soon, like today, tomorrow, or yesterday, really getting serious about this problem, yeah, it could happen again. Thank you.
I've been asked to tell you a little bit about some unconventional liquid fuels, and I'm going to begin with this picture. It's a picture of land in western Colorado, and what's remarkable about this land are two facts. One, it's all owned by the federal government, so this is our land. And about 1,000 feet under everything you're seeing is something called oil shale, and I'll tell you more about that. But under a single acre of this land, we estimate, and so does the U.S. Geological Survey for that matter, estimates that there are about 2.5 to 3 million barrels of oil that can be recovered. And a little bit more about that in a few minutes. But this is an amazing resource. And I press this. What am I doing? Oh, okay, I understand. Once again, oil prices are high. Once again, you're hearing, or at least we in Washington are hearing a lot of talk about unconventional fuels, and they include oil shale, coal to liquids, and biomass. A lot of folks are talking about them as the solution to our problems. It's been raised before, and never have these unconventional fuels been shown to be competitive with conventional oil. So this raises the issue, have unconventional fuels become a viable option? And then what strategies are available to the government to address this? And since where I work, we do a lot of work on strategies, I'm going to share with you some of the ideas that we've come up with at RAND with regard to moving forward here. And I'm going to begin with, can I hit twice or? Okay. I'm going to begin by going through basically a few of these unconventional fuels. The first group is going to be fuels that are called Fischer-Tropsch liquids. Roger Bezdek was referring to those, I believe, when he was talking about coal to liquids technology. And the Fischer-Tropsch family really includes coal to liquids, biomass to liquids, as well as a combination of coal and biomass. And I'll tell you a little bit about that. The only other important domestic option that's available in the near term is oil shale. And when I say near term, by the way, I mean something that you could build in the next 10 years, that you could build a commercial plant. The alcohol fuels, we have food crops. They're already being pushed as far as they can go. The next step on alcohol fuels is lignocellulosic conversion. Our early analysis are showing that lignocellulosic conversion is more expensive than Fischer-Tropsch treatment of biomass. And you heard a little bit about that yesterday, the lignocellulosic stuff right from the Exxon talk. And those concepts for lignocellulosic conversion are not going to be ready for many years. Only the initial plants are undergoing, their pilot plants basically are being built today. So the way I'm going to proceed is give you a quick technical introduction to oil shale and Fischer-Tropsch technologies, then go through some of the key environmental issues, talk about the benefits. Why do we care about this? And we at RAND believe that there's been a lot of confusion with regard to what the benefits really are, and then go into that analysis of the options very briefly with you. And so to begin with oil shale, this is a huge resource. In that yellow box over there, that's the western part of Colorado. To the left is Utah, above is Wyoming. Although that entire area in black is called the Green River Formation, and that small box over on the right corner is called the Piceance Creek Basin. I'm going to point to it. It's right here. And in that entire formation, that Piceance Creek Basin is about 35 miles east to west and about 45 miles north to south. And that entire formation contains about 2 trillion barrels. That's what we estimate is in place in this formation. And we estimate, we had to do our own reserve estimation, we estimate that of that resource in place, over the next couple of hundred years, it's very likely that we could get out at least 800 billion barrels, although we did put a range on it, 800 billion barrels of petroleum. And to put that in perspective, the United States uses about less than 8 billion barrels a year. So that would be 100 years of total U.S. consumption, or it would be 30 years of world consumption, something like that. This is a lot of oil. In fact, 800 billion barrels is 3 times the proven oil reserves of Saudi Arabia. So with Professor Archer's statement, don't worry about oil. The good news is we have a lot of oil. The bad news is we have a lot of oil. And we'll get back to that when we talk about the environmental side of this. In addition, the other big resource we have in the United States is coal. This is a picture of a wall of coal in Wyoming. This is 80 feet thick coal seams. And the seams are actually thicker than this. And that's enough. We have enough coal in the United States to last us at least 250 years, and there's a lot of coal that probably could be discovered and some price increases would come online. So we have a lot of coal in this country, and so does the world. Now, the reason that's such an amazing picture is back in Appalachia and in this central basin here, the Illinois basin where we have a lot of coal, we find 6 feet of coal. That's a rich load of coal. So this is amazing when you think about what we have in Wyoming. Now I thought I'd give you a very brief technical introduction to what oil shale and coal to liquids involved. I'm going to begin with oil shale. This stuff is in the ground. If I showed you a piece of oil shale, it looked like a rock. Someone mentioned if I showed you tar sands or heavy oils, it would be something that was very tarry, wouldn't flow. It would be sticky when you touch it. This stuff, you pick it up, it looks like flagstone. Within each ton of these rocks, and these are these carbon-bearing formations that Professor Archer mentioned, and if we gave these formations another million or few million years, they would turn, all this stuff would turn to oil. But we don't want to wait that long, or some people don't want to wait that long, so their suggestion is let's mine this, dig huge surface mines, because you've got to go down 1,000 feet, and it's 1,000 feet thick, so we're talking about huge mines. So let's mine this stuff, bring it to the surface, crush it, and then put it into something called a retort, which is basically a big kettle, heat it up, do what nature would take a million years to do in about a half an hour, heat it up to about 800, 900 degrees Fahrenheit, and the oil would come out of this rock, we'd upgrade it, send it to a refinery, and that's the scheme. That's the classic scheme. That's the scheme that folks thought they could do back in the 80s, early 80s, the last time we had high oil prices. And there's a new scheme out, which is being pushed by a number of oil companies, including being not pushed, but being investigated by a number of oil companies, most notably Shell, but also Exxon, Chevron, and others. And their scheme says, let's just keep the stuff in the ground and then just heat the ground up, but not over a million years, but over maybe 3 or 4 years. And this method is called in situ conversion. It avoids a lot of the environmental damage associated with oil shale development, those giant surface mines, but it would involve a tremendous displacement over at least the terms, maybe 15, 25 years required to finish a project in a particular area of that basin that I showed you before. When we looked at oil shale, Rand did a fairly comprehensive study of oil shale. We published it in 2005. It's on our website. And the fundamental conclusion with regard to its status, technical status, is that the conventional approach of mining and heating it up on the surface is very expensive, about $75 to $100 a barrel. The environmental impacts are severely limit production potential using this method. We've got this finding, we base this finding on whatever cost information we were able to get, and we've checked it with some major companies, and they've agreed with this range. There are a few small companies that claim they can do it for $15 a barrel, and welcome, go and try. The other approach, the in situ approach, it's not ready now. It's being aggressively pursued. It's potentially competitive with crude selling for about $40 a barrel, but we're not going to know that until at least another 5 years go by so they can finish all their development work. With regard to the other prime contender out there, it's this Fischer-Tropsch method. I got to get... Fischer-Tropsch method. In the Fischer-Tropsch method, one starts with coal or biomass, heats it up in the presence of steam, makes something called synthesis gas. Other people call it town gas. It was the gas used before the pipelines came in. People used gas for lighting in the old days. It all came from coal. And you can take that gas, and they do make it in certain parts of the world, take that gas and make very high-value fuels from it. You can make a zero-sulfur jet fuel or a diesel fuel. You can make naphtha. You can send that to a refinery and make gasoline. And this is the approach that I think Roger Bezdek was mentioning. And the technology was developed. Fischer-Tropsch, the two scientists from Germany who developed the technology. It was used during World War II in Germany, Japan, because they couldn't get oil. It was used in South Africa because of their apartheid policies, and they were worried that folks would not trade with them. And more recently, it's being used to take natural gas into liquid fuels. And and when we look at what we've been doing recently at RAND, you got a call, Jeffrey. Maybe that's me. We've been looking at this combination of looking at coal or biomass or coal and biomass, and we think that all three of these have outstanding production potential in the sense that they could be used to make some millions of barrels a day of fuel. The technical status of all three are about the same. It's not fully green, but kind of close. With regard to coal, the best you can do, assuming that you can capture the carbon, which is not proven today, assuming that you can. I think I've just called South America on this one. So the coal problem, the best you can do with coal, even if you have carbon sequestration, is you can take care of you can match conventional liquids. Of course, with biomass, you can go to you can be literally carbon neutral. You can because you don't need sequestration at all for that. And the coal and biomass combined with carbon capture and storage, we feel takes care of the global warming problem if we can do it, and we think we can. And we think we can do it at some reasonable cost and a lot cheaper than cellulosic conversion. And but biomass alone costs more than the coal, and the coal we find is not cheap, and I'll tell you a little bit more about that in a minute. Environmental issues. Just because oil shale is not with us for another few years, and we've dealt with that very well in stuff that you can find on our website. I'm just going to talk about the ongoing stuff with coal to liquids. The big environmental issue is all right, for coal to liquids, the most serious environmental issue is climate change. A coal to liquids plant puts out twice the carbon emissions as you would find in the entire fuel cycle if you went from conventional petroleum to say, gasoline. So this is a serious problem. I mean, how can you go to coal to liquids if you're going to put out, and still say we're going to do something about global climate change? Water consumption is another problem, but it's only a problem in the West, we feel. The land use is a problem with remining and the ecological impacts associated with coal mining, but that's something that we accept for other reasons. We mine 1 billion tons of coal in the United States. Water quality, air quality, we're not worried about. There have been tremendous technical advances over the last few years. Is this phone still going, or? For the biomass to liquids, the big problem on biomass to liquids is the land involved in producing biomass crops. That's not insignificant. So the big problem is when you have all this huge amount of cultivation of biomass, you're going to run into a lot of land use issues. Talk about the benefits very briefly. We spent a lot of time at RAND trying to understand these benefits because people seem to exaggerate the benefits of doing this. There's a lot of money. There's a lot of problems all over energy with people. Energy tends to be surrounded with hyperbole energy analysis or energy discussions. Our view is that the benefits of any of these unconventional fuels, whether it's coal to liquids or whether it's biomass to liquids, or shale to liquids, or in fact conservation by bringing additional supplies to the market that otherwise wouldn't be there, or taking demand off the market that otherwise would be there. What you do is you lower the world oil prices, and and the economic benefits of that are substantial. Our calculations at RAND show substantive gains with regard to the consumer surplus on just a per barrel basis. In other words, for every barrel of oil you produce, our calculations show that a consumer surplus of somewhere between $5 And I hate to say this range because it's such a huge range, but it's honest, $40 a barrel. And it really depends on whether OPEC can hold itself together in face of demand, what OPEC does, and also what are the elasticities of oil supply and demand in the rest of the world. But folks don't recognize it, and that's significant. A $5 to $40 consumer surplus is significant. It won't be 5, that's the extreme number. There's also a very important national security benefit. I believe that we heard about that last night, of reducing wealth transfers to those oil exporting nations that pursue policy goals that run counter to our true interests. And I point out that neither of these consumer surplus issues, the consumer surplus benefits, or the national security gains due to increased production, they do not are not captured by any firm that invests in the development of these resources. And the other important point I want to make is it doesn't matter whether you produce these extra liquids or you get extra conservation in the United States or anywhere else. It's a world market. Next. Now, there are some benefits that really do count if you build these plants in the United States. First, there's a potential for significant economic profits. The profits from these plants would be broadly distributed because of taxes and possibly royalty payments. At least a portion of them, about 40%, maybe 50% if it's oil shale. There's the benefit of increased resiliency to the petroleum supply chain because all these plants won't be concentrated where we have all our refineries, so it gives us a little bit more resiliency against disasters and natural disasters. And there are some important regional and state level benefits with regard to economic development and employment. Often we hear these employment benefits or these economic development benefits touted as national benefits. They're not really national benefits, they're regional benefits. You're taking jobs from one area and you're moving them to another area. You're not creating new jobs unless you're going to import workers. And finally, I want to go and with this background, briefly go over what we believe are the federal options with regard to all these unconventional fuels at this time. And the key facts that we believe push policy in this area are the following. One, unconventional fuels really do address an important national security problem of wealth transfers from this country to other nations. Very few approaches are ready for commercial development. Crop-based ethanol is already subsidized. You can't do any more for it. The only other near-term option is Fischer-Tropsch liquids, whether it's from coal or coal and biomass, nothing else is ready today and won't be ready likely for 10 years. Fischer-Tropsch liquids may offer economic benefits depending on their production costs and the future of world oil prices. And I want to say a couple of things about production costs of these liquids. We think that the production costs are somewhere between $55 and $70 a barrel. These are not cheap to produce, at least for the first plants. Now later, there will be learning. We know there's a record of strong learning in the petrochemical sector, and we could expect that those costs would go down in real terms over time. With regard to the future of world oil prices, we should expect lots of volatility. We should not expect these prices to stay where they are. And finally, there's the issue that dependence on coal for both liquids and power production may not be a sustainable option, and that all depends on the viability of a technology called carbon sequestration. Can we take the carbon that these plants emit and put it somewhere where it won't harm the atmosphere? And in our view, the uncertainties predominate. One minute. Can I get back? In our view, the uncertainties predominate, the uncertainties regarding production costs. No one really knows. No one's ever done any really good design work on these plants for at least 30 years. Some important work is underway, but it's not done. We don't know about the future of world oil prices, and we never will. That's something we have to live with. And the viability of carbon sequestration just stands out there as not being not being addressed yet. So our view is, what are the strategic alternatives for the government? And we put down a little list here, starting with the conventional role of hands-off, which is the current federal role. That's what we do with most industries in this country. We let them compete. And the other extreme is, go down to the next, is to have a massive program to promote millions of barrels of commercial production. We already have that in place for corn. To me, it's not energy policy. It's agricultural policy. I think most energy experts would agree with that. The idea of going for non-food crops makes a lot of sense. But we're not there yet because we have lots of uncertainty. So we suggest that the right strategy is an insurance strategy directed at reducing uncertainties and getting a very limited amount, but early and quickly getting some commercial experience. So our view is let's go get some of that design work that I mentioned done. That doesn't cost much money. Next slide. Let's get some engineering design done on these plants. Let's put together some incentive packages for just a limited number, a very limited number of commercial plants. And let's make sure that we have a concurrent commitment to address greenhouse gas emissions, and in particular that we can indeed sequester these emissions. That concludes my remarks.
So good morning, and I do realize that I'm standing between you and lunch, so I will try to be as provocative as I can. And in fact, I do have a contrarian view on some of the issues that have been discussed this morning so far, and I'll be sure to point out my prejudices along the way. As Americans, as you know, it is our constitutional right to never be happy with the energy policy that we have. This precept has been in our consciousness for a very long time. We started worrying about energy policy very early in the 20th century, and especially during the Second World War. And we've swung back and forth between trying to be self-sufficient in our needs, or recognizing that oil production in the United States happens to be more costly than it is anyplace else in the world. And so the early policymakers thought that it actually made sense not to invest in developing U.S. oil fields, but I'm going very fast, but to actually import oils from places where it could be obtained much more cheaply. This was the policy through the 1940s, as a matter of fact. And I would point to Harold Barnett, who is one of the founders of energy policy analysis in the federal government. He actually did the first forecast that was ever done of energy requirements for the United States, and that was part of his task at the Department of the Interior. We went from this reliance on foreign cheaper sources in the 40s to an energy crisis in 1973, where we shifted entirely our view of the world from one of international trade to one of self-sufficiency. But I want to mention something that happened between the two. In the 1950s, the Eisenhower administration, acting in reaction to domestic producers who could not compete with foreign oil, actually imposed import controls on all oil coming into the United States. That set of import controls affected most especially Venezuela. And Venezuela, who had been thinking about this for a while, used that imposition of import controls to actually foster the creation of what came to be known as the Organization of Petroleum Exporting Countries, or OPEC. It is U.S. policy that actually spurred the creation of OPEC, and it is that import control that was in place at the time of the first energy crisis in 1973 that came back to haunt us for the subsequent management of that problem. Let's go ahead. the energy independence psychology didn't last actually very long. And the reason for that was that both Nixon and Ford launched these very aggressive federal programs to produce oil and gas from unconventional sources such as coal, and they proved to be such disastrous decisions that they were abandoned within a matter of years. Now, oil is what it is today. Go ahead. The oil sector today is undergoing a sort of a revision of its 1960s frame of reference. That is, the oil companies are renationalizing. National oil companies are emerging from the privatization of the 1980s and 90s and are retaking control over the reserves that the world has. As you can see from this slide, of the top 30 reserves in the world, only a bare 4% is actually in the hands of investor-owned companies. All of the other reserves and the production capacity that is associated with it are in the hands of national governments. National governments do not behave in the oil sector in the same way that private investors do, among other reasons because they rely on revenue from their oil companies to feed their national budgets. There is more incentive to use the revenue for other purposes than to reinvest in the oil sector. Next. That has had consequences for what we have been experiencing in especially the last 5 years. You should know, however, that there are at least 100 countries in the world that produce oil and 80 that actually export it. And in all of this history of dependence on oil, back further to the 1940s, the truth of the matter is that oil has been produced to meet demand. Sometimes has been produced sufficiently in time to meet that demand, but basically oil production has increased in tandem with demand. Today, we are close to 80 million barrels of oil a day, which is nearly twice the size that we were in 1970. So it can actually be argued that the oil sector is meeting its responsibilities to its customers. Next, please. It is true that world crude oil production has some concentration around the world. But I want you to also look at the diversity of suppliers in the world, which makes a difference as to whether or not the oil market itself is competitive or not competitive. And even though the reserves are concentrated in the Middle East, that does not mean the production follows the reserves. It merely means the production capacity is where it is. And in Russia, for example, capacity now equals that of Saudi Arabia. Not that that's necessarily good news for anybody, but the question is that the capacity is very well spread around the world and is a precondition to having a competitive oil market. Now, the problem that's been experienced, especially in the last 5 years, is that the world production capacity does not have any room for error. It has little spare capacity. There used to be spare capacity in a number of countries around the world, but today, the only country that's got spare capacity is Saudi Arabia. It does matter whether or not that spare capacity is available and it is competitively brought into the marketplace or not. There is currently certainly no incentive for Saudi Arabia to use its excess capacity to bring down the price of oil. On the contrary, it is best if they leave it exactly where it is. The world consumes now about 84 million barrels a day. And consumption, as you see, is as diversified as production. North America is still the largest producer, but Europe is a close second behind. And Asia, with the high demand for China and India, is fast catching up with the North American levels of demand. Let's go ahead. The U.S. imports oil, as I said, from everywhere that it is produced. And it is notable, though, that we import more oil from North America, meaning Canada and Mexico, than we do from the Middle East. We always carry in our head this image that the United States is excessively dependent on Middle Eastern oil. Not that it would matter, because the world oil market is global. So if we were not bringing in oil from one country, somebody else would be buying that oil for other purposes. But it is important to know that our dependence is as diversified as is production. Next. You note the actual slices there that we import more oil from Mexico and Canada, actually by far, than we do from Saudi Arabia, with Venezuela being close behind, and Nigeria, a very important part of our current import equation. Next. Back one more. The trend that you need to worry about, that we all need to worry about, is that we are not only importing oil anymore, we are also importing refined products. And note the sharp increase in the volume of import products that we have experienced in the last 6 years, as sharp an increase and a trajectory as we've ever experienced before. But that trend is probably more worrisome than the crude import trend, because products depend on available refining capacity. There are a finite number of refineries around the world, so if anything happens to any of those refineries, prices usually become exceptionally volatile. Next. We have had, as I said, this illusion of reaching energy independence ever since Saudi Arabia and Kuwait embargoed oil to the United States in 1973. As you can see, we've been a dismal failure at this objective, where probably it would be almost impossible to achieve it. But it is such a seductive topic that in virtually every political campaign, there is at least one presidential candidate who wants to promise this chimerical dream of energy independence. The cost of oil does bear on our trade deficit. We already have a very large merchandise deficit. Oil contributes about 30% to that trade deficit and will be growing. Some people think that that's not a very significant thing. Other people think that if that deficit becomes structural, it will eventually have, there will be a price to pay in terms of the value of our currency. Next. In total, we spend about 3% of our GDP on oil, which is not a very large number. And that is the reason why, at this point in time, no one really worries about oil prices running the economy into a recession. It is true that we've had recessions connected with the after effects of virtually every previous run-up in prices, but there has been no indication in the last 4 years of any recessionary tendencies on the part of the economy, even though we've sustained the largest single increase in oil prices in 100 years. And that means that our economy is far more resilient and less structurally dependent on oil than it has ever been. So we can sustain much more problematic issues within the oil sector without driving the economy into a recession. Go ahead. Back one, please. We do make sometimes invidious comparisons with the Europeans in terms of our oil use. Our per capita consumption is higher than that of Europe, as you can see, by quite a bit. And so is our so-called oil intensity, the amount of oil we use to produce a unit of GNP. But the intensity lines have been either steady or going in a downward direction, even as the gross oil consumption in the United States has risen. Next. The most important thing to keep in mind about the oil sector is the incredible complexity and the global nature of the oil market. There is no other market in any other commodity that has achieved this level of complexity, which means that oil prices are set within a structure that is exceptionally difficult to manipulate, except on the margin when OPEC members decide on a reduction of supply, which then has to be redistributed into the marketplace by both physical and financial instruments that are now used to trade oil. The financial instruments that are used to trade oil are several orders of magnitude larger than the instruments that we use to trade actual barrels. So that the trade in oil is now a business worth more than $3 trillion a year, even though the value of the physical oil is only a fraction of that. Next. Obviously, as others have said, our oil consumption is almost entirely concentrated in the transportation sector in the sense that there are no current real substitute for them. The rest of our use, especially in the industrial sector, is as a feedstock to produce plastics and other such things. We use very little oil in the electric power sector, less than 600,000 barrels per year. We got out of that right after the first energy crisis, the second energy crisis in 1979. So if there is an issue of policy with regard to oil consumption in the United States, the answer has to lie in our transportation sector. We have, as other people have said, tried a very large investment in ethanol production as a way to expand our liquid fuel supply. We started subsidizing ethanol production in 1980. We subsidized the investments in every aspect of ethanol, from price support for the crop itself, which in the United States is corn, to the providing tax credits to the investors who build the plants. And we also have in place a 54 cents tariff against import of any ethanol from overseas, for example, Brazil, which produces that product at a much lower cost than we do. Even so, and even with a 25-year investment, we've been able to displace 5 billion gallons of ethanol from a liquid fuel supply of 140 billion gallons. So it took a large effort, above $5 billion in investment, to make only a marginal difference to the transportation fuels that we need. And this is a cautionary tale about seeking to transform a system as complex as that which supplies your gasoline at your local station. It is a system that spans the world, has been optimized to deliver a product that, relatively speaking, is actually fairly cost-effective. The average American pays more for a cup of Starbucks than they do for a gallon of gasoline. And the effort that goes into producing each has really no equal at all. So to conclude, I think the important thing to remember about oil policy is that it has always been difficult to make to the satisfaction of most Americans, or to make a difference in our reliance on oil, first of all, and on oil imported from other sources as an important component of it. It is not for lack of trying. We have tried on several occasions, beginning first with the Nixon and Ford administrations, and even more so subsequently in the Carter administration, to find alternatives. And well-meaning people who were very savvy about the energy sector made very strong decisions that have cost a great deal of money to try and remedy that oil equation. All of them, virtually all of them, stopped in time to realize that neither the economics nor other aspects of it were going to be able to make a significant competitive challenge to the oil sector. That is not to say that we need to accept the world as it is. It is only to say that there is a difference between aspiring to a different energy structure and the actual process of achieving it. The process of achieving it, in the case of oil, has always been more difficult than our ability to dream about it. Thank you very much.
I'd like to invite all the panelists back up we'll have about 25 minutes of questions. So there's a microphone right in the center there. If you have any questions, please stand and approach the microphone, and feel free to ask any of the panelists or all of them.
Question in regard to oil shale and also oil sands, if you wish to address it. Where does the energy come from to release this material, to release the petroleum from the shale, from the sands, particularly in the in situ approach? And where does the water come from for these processes? Anybody who'd like to address it? Thank you.
For the in situ approach, the energy basically comes from the oil shale itself. The part of the oil shale would be used to, well, part of the liquids or the gases produced by the oil shale process would be used either to heat up a fluid that would heat the ground up, or to make electricity, and the electricity would be used to heat the ground up. So for the oil shale production, nearly all the energy would be used from oil shale. Your question really derives from a debate with regard to ethanol fuels, and the what we've tried to not worry about how much energy. I think how much energy goes into making a fuel is sort of not very relevant. What's relevant is what kind of energy goes into a fuel.
Well,
let me finish.
A lot of people think it is relevant. I mean, do you have to supply? Are you using up half of what you get out, or 90% of what you get out in creating the product to begin with?
It depends on which process it is. You use about 1/3 to 1/6 early on, maybe less later. But remember that it's really the quality of energy. Are you using oil to make oil, or are you using something that's much more abundant? When we make electricity, we put about 3 units of energy in, and we get 1 unit of energy out. So we use a lot of energy to make electricity. It doesn't mean we shouldn't use it. We would like to be more efficient on it. The reason this has come up is because folks have said that ethanol is not an energy efficient process, that we use more energy or just about as much energy to make a gallon of ethanol as we do. It takes as much energy to make a gallon of ethanol as you get out of it. And that's really not a useful concept. What really counts is how much CO2 you make when you make the ethanol, and how much premium energy you use when you make ethanol. Are you using oil or using natural gas, which are scarce fuels in this country, to make ethanol? And when you look at it that way, ethanol doesn't look as nice as some of the other fuels, but it depends on whether you make it from food crops or whether you make it from biomass residues or crop residues. With regard to water use, the water would have to, that's a big issue. And there's aquifers there. We don't know. No one's done a design of an oil shale plant. There's a lot of hand waving. No one's done a detailed design. None of the folks who are investing heavily, like Shell, have done a design, or at least have published a design saying, here's how we would do it. So until they do that, we don't know how much water they're going to take from the Colorado River Basin and how much they're going to get from aquifers. It's a problem in the West.
I have actually two questions that were raised by Vito's presentation, and I wonder if you or others on the panel could expand on them. The first has to do with the way that you argued that this last oil price shock has been absorbed so successfully by the U.S. economy. And there are some economists who argue that that's because of the way the housing market actually worked and the credit markets as well, that in fact we don't know how well this shock will over time be absorbed because it was actually mitigated by the use of credit and the spending inside the United States. And I wonder if you could comment on that, which is my first question. And my second question has to do with refining and whether you or others on the panel can explain to us why there is such a clear refining crunch going on, or it appears to be a refining crunch. What's the origin of that, and what is the prospects of actually dealing with that such that we may expect further price shocks just from the refining problem?
Well, I'll give it a first try. I believe that you're right that there is a debate in the economics community as to whether or not this last run-up in oil prices is eventually going to show up in some way. In the previous cases, 1979, even 1990, in the 1990s, just before the Gulf War, prices went up probably by $10. This time they've gone up by 40. In the 1990, the recession was almost predictable. In 1991, it came just as expected. So people are puzzled by why that was so in 1990, the last time, and why it does not appear to be detectable now. Some people believe that part of the problem is that oil prices are not part of the measure of the structural inflation that the Fed uses in order to monitor all of this. And there is some argument for that. But the Fed has been very conscious of the oil price increase and has adjusted its rate policy to respond to this, as was the lesson learned over the previous 20 years. So I wouldn't conclude in absolute terms that we're not seeing this recession, but it's certainly the economy is reacting differently than it did each time in the past. On the refining side, I think that there are two fundamental forces that have been at work that make the refining sector as problematic as it is. One is that we have not built a new refinery in the United States since probably around 1979 because it is exceptionally difficult to site a new refinery. So the refining owners have preferred to expand capacity at existing locations rather than seek new locations to build new ones in. There was also for quite a while and through most of the 1980s actually excess capacity in refining, which spurred a consolidation of the industry. But I think that what has shaped the current structure is the Clean Air Act of 1990, which mandated the production of reformulated gasoline differently for summer and winter. And the standards that are used for the reformulated gasoline were originally recommended to be national ones so that gasoline could be traded across borders. For reasons that I've never been able to understand, although I did work on the Clean Air Act of 1990, the EPA, the Environmental Protection Agency, refused to issue a national standard and allowed states in different regions to propose their own. So what we now have are actually mini markets for reformulated gasoline that are tied to particular regions with no spare capacity and no ability to fungibility of that market. So that if something happens in a refinery in the Midwest, we cannot import that formula gasoline and sell it within the Midwest. We just have to bear the higher price and live with it. I think this is actually a resolvable issue that policymakers have just simply failed to do by merely being deferential to state preferences. Now, states are paying a very large price, in my view, for having chosen that course of action, but it is a resolvable issue, and policymakers should do it.
Let me add 2 points quickly to that. First of all, until quite recently, refinery operations have been a low-profit business. The energy companies have not been anxious to expand or build new ones. Secondly, I was fascinated by Scott Newman's presentation, the fellow from ExxonMobil, yesterday, where he pointed out that they foresee most of the increase in demand coming from countries outside the U.S. That's where they're building their refineries in the future. Very interesting point.
I'd like to comment on the economic question you asked. Economists like to talk in terms of GDP. We also need to consider, consumer surpluses. What does it do to your own pocketbook? And it's very easy to show that a $10 barrel increase in the price of petroleum basically costs the average household in the United States about $700 a year. So that means, and oil's going up a lot more than $10 a barrel. So could we use 20 million barrels? It's baby math. So we're talking about less disposable income per household of thousands of dollars. I mean, it's gone up at least $30 more than one would expect it to be these days. So that's a major impact. So it may not be showing up in terms of gross domestic product, but it's showing up in the fact that the gross domestic product that we're producing isn't staying with us. It's going out of the country, or it's going to our own oil producers. And with regard to refining, I think we are there's been a fundamental change in the industry. You appropriately described the excess capacity we have. The refining sector views the fact that we have now 93%, we're running at 93% of capacity, as a major business achievement. They were running at 80 to 85% of capacity for many years. So they're very happy to be where they are. And there's no obligation in the refining sector today for sure supplies. That is gone. This is competitive business, and it's gone. And I think it's something that needs to be revisited. It needs to be revisited. And I start that revisit by going to the companies and saying, look, we're not going to put up with this kind of price volatility associated with refining. What do you propose? And it may be more interregional pipelines that we need for products. It may be getting, rationalizing some of these boutique fuel standards. It may be some combination of things. And it may be, as someone mentioned yesterday, setting up a product reserve so that there's ways to get gasoline. I don't know what the solution is, but I think it's worth looking at.
Well, as a matter of fact, it has been looked at. During the 2005, Congress was considering the Energy Policy Act that finally was enacted and offered refiners incentives of various kinds to build new capacity, including allow them to locate on federal lands if that's what they wanted. But it has been the consistent position of the refiners that if they need any help, they will ask for it. Now, it's very difficult to impose a requirement on the industry on the part of the federal government because previous requirements that we've imposed on them have typically backfired. Now, the refining business is not the most profitable part of being in the oil sector. And I think that's part of the critical problem involved. A refinery is a very expensive proposition. It requires enormous maintenance. When it goes down, the losses are huge and the profits are thin. So until we find some other sort of physical structure to do what we do, it seems like a difficult thing to resolve. Except, as I said, for the self-imposed micro markets that we've established for reformulated gasoline, which serve no purpose whatsoever.
Just to offer a comment on this same issue, which is that it's really a global problem. CIRA, Cambridge Energy Research, did a study on it and found that U.S. refining capacity actually increased ahead of demand. But Europe is moving to very efficient diesel fuels, so they use the middle of the barrel, the light, sort of the light sweet crude. And the former Soviet Union refineries have closed, and there aren't new refineries in Asia, and there's plenty of heavy crude, but not a lot of deep conversion refineries that can refine it. So actually it's the move to efficiency and the move to cleaner air in parts of the world other than here that are squeezing competition for light sweet crude and making this, the spread between the value of them so wide. So it's actually not a problem that we can significantly fix here in the U.S. and that we can fix significantly by regulation, because the problem, the capacity needs to be in Asia and it needs to be in Europe, and that's why Exxon has spent 15 years trying to build a deep conversion refinery in China. But there's not a whole lot we can do in terms of U.S. policy to drive other parts of the world to deal with those problems. So we're in a sense it's part the law of unintended consequences and part kind of out of our control.
Just to give the audience a handle on this, back in 2000, the refining markup, the refining component of your gasoline cost was about 15 cents a gallon, running around that number. I'll bet today it's closer, and I haven't seen the latest data. The Department of Energy publishes it, but it's about a month and a half out of date when they publish it. But I'll bet today it's about 70 cents a gallon. So about 70 cents of what you're paying for a gallon of gasoline is for the refineries. Now, 15 cents wasn't covering the replacement cost of new refineries. That was probably too low, but 70 cents is probably, too high. So somewhere in between, probably closer to 15% is the right number.
The trends are very worrisome. As you saw in one of my slides, we were importing about 1.5 million barrels worth of refined products just 10 years ago. Last year, we were at 3.5 million barrels. This is not crude oil. This is gasoline or various other kerosene and other products that come from Europe, come from Central America, come from South America, and that substitutes for all of the capacity that we do not have in the United States. So not only are we running a capacity within the United States, but we are the driving force for demand of these products worldwide.
Professor Archer said that to first order, we could mitigate some of the environmental consequences of oil if we just avoided coal. But the two countries that were most dependent on coal were India and China, and simultaneously there's the least amount of oil reserves in Asia. So if we say, let's not use coal, we're really saying, China and India, you need to do your part too, and then what energy sources do they have? Do we want them with a whole lot of nuclear plants? They don't have a lot of rivers to dam up. How do we, as policy, how do we deal with this no to coal issue?
Well, I'm not a political social scientist. You're absolutely right about this being a global issue. It's not something that the U.S. can solve on our own, but it seems to me that if we have the infrastructure, the smart people, and the money to develop the technologies to do other things with coal. So IGCC, integrated gasification, combined cycle, is a more efficient way of getting energy from coal that produces CO2 in a pure stream that can be sequestered. Carbon sequestration is still kind of the frontier too, as we heard this morning. We could invest in learning how to do that. And then maybe other parts of the world could sort of leapfrog technology. Instead of building old technology plants, they could build new technology plants in the same way that some parts of the world never built land telephone lines. They just jumped straight to cell phones. So I would say the policy initiative on our end should be to develop these technologies and make them more off the shelf and make them available to other countries.
I had two questions based on Mr. Stagliano's presentation. The first one was geared towards the graph that divided up consumption by sector, and transportation being the biggest sector here in the U.S. How realistic would it be for a U.S. policy to say that air, rail, sea, commercial trucking, transportation, public transportation must be 100% dependent on alternative sources of fuel. And then the second question was on your history of the administrations, the presidential administrations. How did President Carter drop, I think it was just 1 or 2% in fuel consumption or oil use during his administration?
Congress has considered several pieces of legislation to mandate that fleets, especially of vehicles, and companies that use large fleets should be required to have vehicles that are fuel flexible. Not necessarily to use an alternative fuel, but at least that they're fuel flexible as the beginning of a down payment into making the entire American fleet, which is now 300 million vehicles, at least capable of using something else if that something else ever becomes economic. There was a piece of legislation passed to that effect in 1986, but we have vehicles in the country that are fuel flexible, and there are some vehicles that are fuel flexible without their owners knowing it. So the idea of this fuel flexibility did not get very far. It would be exceptionally difficult to mandate it unless we were prepared to ensure that the alternative was as economical or nearly as economical as the oil that it displaces, and we're not in a position to do that. The best we've been able to do is to use compressed natural gas and ethanol in some vehicles and subsidize their use as well as their the conversion of the vehicles. We even have tax incentives available to retail gasoline stations who want to build a compressed natural gas station or an ethanol station. And there are some around, including in Illinois and in the Midwest. But at the large scale that we would need in order to make a difference to that 140 billion gallons, I don't think that the federal government or the state's government are ready for a mandate. They can encourage greater use of ethanol mostly or CNG, but I think we're some distance away from mandating this requirement. On the issue of what happened during the Carter administration, one of the charts that I showed a dip in demand around 1985. The only one in that trajectory that has been steadily going up. There was only one dip in our history in demand, and that's in 1985, and that was due to the combined consequences of our having imposed fuel efficiency standards for automobiles in 1979, which made their way through the fleet by 1985 and went from an average of 13 miles per gallon for light vehicles to 27. And secondly, we banned the use of oil for most non-essential reasons, including by industry and by the power sector, through a thing called the Fuel Use Act, which we've since repealed. The combination of this banning of oil use in non-essential sectors and the imposition of the fuel economy standards gave us that little break in 1985, which not incidentally coincided with the collapse of oil prices. Oil prices in 1985, if you can remember, were $9 per barrel.
I would just...
I just want to give you a little perspective on unconventional fuels, because we've spent a lot of time looking at this. I mean, first, that huge amount of oil shale I talked to you about. Our estimate is that with an extremely aggressive program that would cause inflation in the construction world, after the first plant is ready, after folks start to build the first plant, which we think is 5 years from today, it would take about 30 years for us to get about 3 million barrels a day of production out of that resource. And remember, we use 21 million barrels in this country. So unless we want to do an all-out program that I believe would cause massive amounts of inflation in this sector, it's going to take time to do these things. So when we look at oil shale, we say, from today, maybe 35 years, we might get 3 million barrels. When we look at coal to liquids, there's a whole range of possibilities. The technology is ready now. It depends on how much push you want to give. But if we went fairly aggressive on coal to liquids, by 2030, we might have 2.5 to 3 million barrels a day. Might. That's even pushing it. And again, that's, so 1 million barrels of oil shale, a couple of million barrels of coal to liquids, 3 million of coal to liquids. That's not much. We look at alcohol fuels from food. If we push that to the extreme, we don't think we can get more than 1 million barrels of alcohol liquids. So that's 5% of the liquids problem. And yet, and what bothers me the most is that there's so much attention by our Congress on alcohol liquids when it's not a solution. It's a small piece of the solution. I'm not saying that you don't want to do it, but to put all of our efforts into something that is not there. And yet, the real options, the real options that take political will and guts were mentioned yesterday, and that's to you want to take care of all this? Put a tax on oil. And the marketplace will take care of it, and we won't have it coming out of our budget. It won't be constituent services and gimmicks by the Congress to take care of their own constituencies. And we'll solve our energy problems. We'll solve the national security problem, put a tax on CO2, and we'll solve the global warming problem. And if you don't like the tax because it's regressive, then give that money back to the people in their tax returns. Or reduce Social Security taxes or something like that. There's lots of ways to handle it, but no one wants to do what is really required. And that's been going on since I was involved in energy in 1978. Just gimmickry.
I would just point out very quickly that fuel economy of our automobile fleet has been getting worse over the years because we drive bigger and bigger cars as a sort of fashion statement. I think we could easily get a factor of 2 improvement in fuel economy technologically. That's available now, probably more than that if we worked on it. So, all of this sounds intractable and like forces of nature we can't possibly fix, but I think it would be much easier to fix by just making cars go better.
But any and all of the options that have just been discussed will take decades to have a significant impact on the U.S. energy situation. Options both on the demand side and the supply side. There are no quick fixes.
Good morning. Babette Payton, filmmaker, Freedom at Sunrise, the movie that will be out this August. First of all, I want to say thank you to the Chicago Society and the University of Chicago for having this wonderful forum. I was here last night and I thought the speakers were very provocative. And this morning, the same, making you think, information, and some of the speakers I've met out in the hall. My question is threefold. It's one question. It deals with the things that all of you have talked about the future. And since we're here at the university, we have a lot of students here, some interested in chemical engineering, some interested in energy, some interested in a lot of things that are going to make a difference in the future of our energy, our petroleum, our policy. My question has to do with small businesses, because some of us will go into small business. I think the federal government has a program dealing with small business innovation research and small business technology transfer. So my question is, do you think that there are any opportunities for maybe even some segment industries or products that could be developed for commercial purposes that maybe someone from this audience might become a proprietor, might develop, as a patent or patent for a process? As we look in this room here, we have the auditorium, and we have the chairs, and we have the table, and all those things. So they're all components. We don't have to do everything, because I know you were talking about the cost of the large infrastructure, and most companies are now trying to just expand where they are. Could you shed any light on that in terms of opportunity, options, or suggestions that some of us might think about in the future for diversifying, I guess you could say. Thank you, and thank you for everybody for being so wonderful.
Anybody want to?
Well, I'll take a partial stab at that. One of the problems the country, the energy industry faces over the next decade at least, is that from the early to mid 1980s through until very recently, enrollments in fields dealing with or related to energy just cratered in most colleges and universities around the country. In some instances, the number of people enrolled in petroleum engineering, petroleum geology dropped by 90% from their 1982 highs. Departments of nuclear engineering were actually disbanded in many universities. During the 1990s, the oil and gas industry shed 500,000 people. Now when we're talking about all these initiatives in alternative fuels and conservation, biomass, coal liquids, nuclear, oil shale, what have you, the warm bodies simply aren't there. So I would encourage people at this university and others to get into the energy fields, chemistry, biology, physics, math, engineering skills, computer science, what have you. With respect to small businesses, I don't know, I'll let the other panelists handle that if they feel qualified to do.
Well, there's plenty of small businesses involved in the energy business, and whether it's coal, oil, or gas, there's an abundance of small businesses that serve as suppliers and innovators and technology developers. So that's already out there, and the marketplace is taking care of it. There's a lot of government assistance for some of this, but for the most part, those that are successful have a product that they can sell. With regard to Roger's statement, I agree with him that we need more folks who are smart and are well trained in the sciences and engineering, especially geology, if we're going to be doing carbon sequestration. But on the other hand, my best advice to you is major in what you love, because the market gets bad for your particular field. You'll always be happy doing it, no matter what.
I can tell you that you might want to stay away from energy policy making. That's the most frustrating thing of all.
I would put on a technological wish list better batteries for cars, electric cars. I think that's what's pacing the development there, and energy storage mechanisms to store energy from intermittent sources like wind and solar. If they were better, that's sort of holding up development there. The Danes in Denmark are pushing the envelope of wind production, but they give away something like half of the electricity they generate from windmills because there's no way to store it, and it comes in a time when you don't need it. So that's a hurdle that if somebody wanted to take care of, that would be most nice of you.
Can I just ask a question to bring us back to the University of Chicago for a second? There's been a lot of sporadic criticism of government policy in the energy area. With regard to ethanol, big cost, not a lot of payback. Some of the other fuel efficiencies, other things like that with unintended consequences. If you look back over the last 20 years, has government policy been a net positive or negative in terms of the availability and cost of energy? And going forward, should we just let the market take care of energy policy?
I experienced service in the Department of Energy in both the Carter and Reagan administrations for a short time in each of those administrations. As you know, President Reagan wanted to eliminate the Department of Energy. And as I look back on it, I'm not convinced that was a bad idea. I mean, it wasn't a bad idea. I mean, there's something to be said. I mean, why do we need an energy department? We need research in energy, but the current energy department we have, doesn't really do energy. I mean, that's the least thing they do. They run the nuclear weapons development program for the United States. They operate a bunch of mortgagee laboratories that are left over from the Manhattan Project, including one that this school manages. And I always believe that every country needs a good national lab, and we've got a bunch to sell. And no, but one of them is not that kind of lab. We spend $2 billion a year in energy R&D. And you would be hard-pressed to identify a single product that came out of that. I can tell you a few, but it's been a fairly low return on the investment. A lot of that is because the system that we have here in this country demands that the Department of Energy produce things fast. So, the photovoltaic program, for example, which is a real challenge, a really tough program, real tough challenge, that program has consistently promised a product in 5 years. And they've been promising that product in 5 years for what, 35 years now? They should have put together a research program that recognized how hard it would be to solve that problem. But because they were always looking for fast solutions, they haven't made that much progress in that problem. And so I don't know, when I look back on it, whether over the long term we needed an energy department. Now, things have dramatically changed in the last 5 years because there's been a much greater recognition about the national security consequences of this massive amount of oil going abroad, although if you go to the Department of Energy, and we've got people here who are familiar with that department, the department doesn't do much about that. All right? I mean, it's really not a big department function. I mean, when oil was $9.50 in 1998, the folks in the Department of Energy were very upset because no one needed them anymore. All right? Now, they weren't claiming victory. They were depressed. And the other big issue is global climate change. And now we're seeing that we really do have before us a major transformation that has to be made over the next 30 and 40 years. And I really do now believe that we need a department that does address that. The question I have is, does the Department of Energy, with all of its other functions, the weapons, the legacy of the nuclear waste disposal problems and cleanup problems, is that the department that we want to do this, or should we have a better department that's focused on this really major, massive, important transformation that we're about to move towards?
Well, at the risk of sounding self-serving, because I did spend 17 years of my life in the Department of Energy, I think that the options are limited in terms of what the government should accomplish in the energy sector. And I would distinguish between policy and the rest of the stuff that the department does. Remember that 60% of the Department of Energy's budget goes into managing our nuclear weapons complex, which is not an option that we can delegate to anyone else. The other parts of the department have to do, in fact, with research and development efforts. And one may argue about whether or not the majority of those efforts bore fruit or whether they would have borne fruit by some other means. Most of the R&D that takes place in the Department of Energy is actually in conjunction with the private sector. They're usually jointly funded demonstration projects. But the country did inherit this dozen or so national laboratories, including Argonne and Fermilab here in Illinois, that had original purposes very different to those that are used today. The trouble that the national labs have is that the Congress can never make up its mind as to what it wants them to do, and juggles its budgets on an annual appropriating cycle that does not allow them to really build institutional capabilities that are long-term in nature. So I would say that it's less a matter of what the research and development structure of the Department of Energy wants to do than what it is allowed to do by this very Byzantine way in which Congress spends money. Someone has to do that research. A good deal of it happens in the private sector, but a good deal of it does not happen in the private sector because in the energy field, the private sector is mostly on the investment side of the equation rather than the R&D side of the equation. So it's always possible to reform what we have, but the signal is in the hands of Congress.
Well, it's interesting to note that when I got into this business, we actually had an outfit in the federal government that did energy research. It was called the Energy Research and Development Administration, which eventually became part of DOE. As Yogi Berra once famously said, it's deja vu all over again. There are now ideas on the Hill to create or recreate what they're calling the DARPA, Defense Advanced Research Project Agency for Energy, otherwise known as the Energy Research and Development Administration, which we had over 30 years ago. I think it's worth considering because, as the speakers have noted, the Department of Energy does many things. A small priority of that is energy research. After ERDA became part of DOE, it really the R&D function got lost in the shuffle. As to whether any of this R&D is paid off, my company has been working over the past several years with the National Academy of Sciences trying to address that question at the mandate of Congress. Energy research at DOE, was it worth it? And we've identified a number of projects that actually had quite a large payoff, some projects that had no payoff, and many that were in the middle, similar to one stock portfolio. Some stocks in your portfolio will do spectacularly well, some will do very bad. Most are somewhere in the middle. The problem is you never know what the winners are. Always know in hindsight, but not when you're starting the program or the investment.
I would just add briefly that from a climate change perspective, the free market is not going to be capable of solving the problem because it's a sort of tragedy of the common situation. The cost of climate change is what they call external to the decision-making process of the person. So the person, gets the benefit of driving the car but doesn't pay the full cost of the climate change. So from the climate change perspective, free market is a recipe for a train wreck.
Nor will the free market necessarily successfully address the energy security issues.
That's why you put taxes. That's what taxes are about. Or caps and caps.
Never happened.
You're probably right.
Well, thank you very much to all of our speakers.